Hello, everybody. Thank you very much for the kind introduction. I will speak about actuators for robots interacting with humans and unknown environments. And our primary motivation as an institute working in space is to design robots which can interact with really completely unknown environments like planets and moons, or are able to interact with humans, with astronauts, to solve complex manipulation and repair tasks. But of course, generally, the idea of having safe and reliable helpers to human is as old as robotics, and Isaac Asimov's literature with his famous laws of robotics made this popular. And actually, in direct line strictly related to that are some science fiction movies. One of them just playing in Chicago 20 years from now. In the upper corner, you can recognize probably the structure of the loop. And I have chosen some sequences because this movie carefully shows what we would like to have from such robots. You see here, robots should be safe and reliable to humans, should solve tasks which are dirty and difficult to be done by humans, should solve some tasks with higher than human performance and being a good companion. And of course, we would like this robot to move at velocity and performance, which is similar to humans, but probably most of robotic people watching this movie ask themselves, what would I put into that actuator to have a robot which is that slim and as fast as it is today? And will we succeed in 20 years from now to build something like that? So this is what my talk is about our activities towards actuation. And I would like to highlight mainly two perspectives, actually, in our evolution. And we invested in the last 20 years some time in designing lightweight structures where we focused on the mechatronics design, integrated modular components. And the main feature is the fact that they have software-based compliance using torque sensing. But in the last 10 years, we more and more focused also on systems which are even more inspired by the biological archetype by trying to mimic the intrinsic compliance and the antagonistic actuation from biomechanical systems. And the scientific challenge is there on one side to understand human motion and neurocontrol, and on the other side to use these principles to build even better and more efficient robots. So just to summarize the technology which is today considered state of the art, and we were one of the institutes pushing this technology forward, it's to say so, standard mechatronic design in the sense that we have brushless motors, which are, however, optimized for high torque at low velocity, harmonic drive gears, but most important, we have the torque sensor, which is placed after the gearbox and allows for compensating of friction and reducing the inertia, such that you have an almost ideal torque source, which has been the dream of robotic control designers for many decades. And still, these robots intrinsically, parasitically, to say so, have some compliance. So you need the torque sensor also to compensate for this elasticity. But this comes parasitically with the lightweight design and whatnot introduced by purpose at that time. But still, we had to learn how to deal with this compliance, and there has been some seminal work of Alessandro De Luca and Mark Spong, which helped us in that way. And on top of this torque interface, we have compliant control. Again, based on great work of Neville Hogan and Osama Khatib. Stefano contributed a lot to compliance control. The basic idea is that you have virtual springs, which you attach to the rigid robot in order to grasp objects. You would attach springs to the finger to the middle of the object. And then you would transform those virtual spring forces to joint torques. And this is a very simple concept, but can be hierarchically extended to grasp with two arms, to move objects around in several hierarchical structures. And you always do the same. You compensate gravity mostly based on motor position, but you have to take into account elasticity. And then you have one component which is related to the derivation of the elastic potential, and by deriving this with respect to the joint torque, you provide, to the joint position, you provide joint torques, and then you add some damping. This is pretty simple, but we extended this over the last years to more and more complex structures, like the humanoid with 43 degrees of freedom. And here you can see hierarchical tasks, the robot holds the position, follows the human, avoids the collision with the second human, avoids singularities, controls the posture, and so on and so forth. But you have to keep in mind that all this structure is purely implemented by control, and the robot is more or less rigid. You can use the torque sensing also to detect collision with high accuracy in order to provide a safe robotic system, and this was what we had to deal with when commercializing the lightweight robot structure or the lightweight robot technology with our partners from KUKA. And this technology, because of its modularity, so basically the whole electronics and mechanics is placed within one module, could be extended to more and more complex humanoids like Justin, also to other application areas like medical, and as mentioned, we spend a lot of time in commercializing this technology. Many of you know the robot. The last prototype I would like to show, because I started by motivating with humanoids, is the work done by Christian Ott and his group by integrating the lightweight robot components into a humanoid. And he started this work after spending some time in Japan, in Yoshi Nakamura's lab, and basically extended the work we've done for manipulation for several years on balancing on uneven ground. And intuitively, it is clear, but he has methodologically shown that basically grasping and balancing are closely related. Basically, it's a dual problem, balancing as you would manipulate the ground. Of course, we are not the only ones doing humanoids with torque interface, especially on hydraulic actuation. There has been some very impressive work starting at Sarcos and the newer work with Atlas's Boston Dynamics. And they have hydraulic actuation, which has also precise torque sensing. And all those robots have in common that they have very good control performance. However, they have limited power to weight ratio, and this is particularly true for the electromechanical actuators. And this was also one of the main messages on the IROS workshop on actuators, where we could see that many designers still struggle to design actuators which preserve the performance of electromechanic actuators or the performance of electric motors, which is very high, but this performance drops as soon as you attach gearboxes and becomes much worse than human performance. So still we are searching for ways to improve the torque at low velocity in order to achieve biological performance. And one other drawback is important for those systems. If you look to those pictures, and those people working with these robots know, you will notice always that you have a cable suspending those robots for preventing them to fall down. And everybody knows why, because if such a robot falls down, the control compliance is not fast enough to react, so most probably the robot will be damaged. And this is seen in this unfortunate video of Asimov, which, however, is probably the most advanced humanoid. But you notice that all the controlled compliance, all the adaptability disappears as soon as software or hardware fails, and then you have a rigid piece of metal which probably will break as soon as it falls down. And this is, of course, in striking contrast with what humans can do, well, at its limiting or high-end performance at its time. And this motivated researchers over the decades to think about deliberately introducing elasticity in the system. And it's easy to see why on this picture showing parkour's athlete. He uses the elasticity of the tendons and of the muscles first to store energy when jumping and producing an explosive motion, and on the other side to absorb energy at the impact when falling down, and to limit the peak torques at the impact in order not to damage the muscular structure. And in the early 90s, this idea appeared mainly in groups in the United States, and here are some images showing serious electric actuators. They had a big advantage of being able to provide a torque interface in pretty good quality, although probably not as good as with a torque sensor, but they help reducing impacts. And they have a relatively simple design. You have only to introduce an elastic element in series with the structure. And we have here several examples from manipulation but also from locomotion. Some videos kindly provided by Jerry Pratt showing the hopping flamingo and the humanoid. Interesting technology. One drawback might be the fact that due to the very high compliance, bandwidth is limited. So as soon as you would like to do a very fast motion to react quickly, this is a limitation. And high accuracy in positioning is also a challenging task. We have seen that even for the lightweight robot, it's a challenge to deal with the compliance. In a compliance structure, this is even much more difficult. And this motivated groups worldwide, and particularly a pretty large group in Europe, to think about systems which are more inspired by the biological example, by looking at the way antagonistic muscles are used in biology to generate motion and robustness. And we have antagonistic muscles which can move the joint, but can also co-contract to change the stiffness. And well, a simple example how you can translate this into a mechanical system is using two motors with two tendons. And by moving the motors, we will move the link. You need a nonlinear elastic element, but by pre-tensioning the string, so by increasing the tension in the cables, you could increase the apparent stiffness of the system. And most important, if you if you have an impact on the output, as in the video below, this impact goes directly through the springs and will not affect the motor, preventing the system from being damaged. Of course, this basic principle has one drawback, that you have two motors and you have the torque of just one motor in each direction. So you are wasting space and volume compared to classical actuation. And that's why we spend in several European projects a lot of energy in designing different concepts to avoid these problems, to reduce to the power-to-weight ratio of the systems, to increase performance, to reduce friction, to increase efficiency. And we had prototypes based on pneumatic actuators, also some hydraulics, a lot of electromechanics, variable stiffness, variable damping, even new soft actuators like electroactive polymers. And actually it turned out that it's difficult to design one actuator for all applications, but rather it will be the case that for specific actuations or actuation situation, you will need different prototypes. For example, one solution which has been adopted also in our prototypes and also in Antonio Bicchi's prototypes is to use the fact that motors can not only pull, but they also can push. And by closing the wire loop, you can use actually both motors to hold heavy loads, and then you can take use of the whole mass of the actuator for holding and moving around heavy loads, while still you can co-contract the system to change the stiffness in the way described before. And again, the impact goes to the springs and not to the system. Another way to save weight, if you don't want to change quickly the stiffness, is to use one large motor, for example, with harmonic drive gears, to move the joint, and then just use a smaller motor with high gear ratio to pre-tension the springs and then change the elasticity of the system. But obviously, each design has some advantages and some drawbacks, and it's hard to compare them by just one number as we thought initially when we started this work. Instead, we had some very intensive debate and came out with a list of characteristics which describe this kind of actuators. So in addition to the classical power, torque, velocity, and so on, you need, for example, to describe how what is the stiffness range of the actuator and how the stiffness range changes when the torque changes, how fast you can change the stiffness, what's the maximal energy you can load on such a system, and so on. So we came out with a standard data sheet, and you will find on our project website and also on the Natural Motion Initiative website, meanwhile, I think, the description of more than 10, about 15 actuators in this standard way. So this should make a comparison easier and also a choice of an appropriate design for your application. Just two examples of very, very different applications. Actually, at DLR, we focused on highly integrated, very complex prototypes in which we try to mimic the performance of the human arm as good as possible. In contrast, the group in Pisa is focusing on commercializing systems and providing to the scientific community systems on which they can develop software and controllers and which are affordable in the low-cost area. And of course, the systems will then look very differently. For example, in our case, we have only in the forearm 90 degrees of freedom, in the hand 38 motors, 7 degrees of freedom in the arm. This leads to a large number of actuators, of course. So for the whole dual arm system, we have over 100 motors. And because this is a first system which we built and we wanted to experiment with different designs, we introduced this antagonistic actuation, but also this helping antagonistic actuation, and also the design with a harmonic drive with a small gear pretension, just to have a comparison of these different approaches. And here I show a video which we developed for the Automatica fair last spring, showing the main features of variable compliance actuation. This is a task in which you, first of all, you have to grasp an object and hold it robustly also during impact. Then you have always a hard impact of metal parts which would damage standard robots. Then you are using dynamic motion. Actually, this is done in resonance by using the springs. And still, this is very precise and repeatable. You can see that we have, by a learning technique, accuracy below 1 millimeter by using iterative learning control. This is the DLR logo, which has been printed there. So I think altogether, you need variable compliance to have all these features in one system at the same time. Again, some videos summarizing the main features. Robustness. You could not do that with a rigid robot. You need serious elastic actuation or variable compliance to be able to withstand such kind of impacts. I mentioned before, control cannot react so fast. Explosive motion, storing the energy in order to throw objects is also essential to have compliance for that. And what we focused more and more in the last years and months was cyclic motion generation. I gave a talk at the workshop on Sunday, so I won't go into too many details, but I think variable compliance and compliance actuation in general is essential for this kind of motion. And we noticed that still the community has difficulties deriving controllers and planners which really excite those elastic systems into resonance. And the reason is that we are still lacking a very precise mathematical description of resonance of nonlinear systems. And optimization tends to take very long and breaks for many degrees of freedom. So that's why we did some experiments, but we try to understand why animals, and in particular humans, are so good in exciting elastic motion. And the experiment was using a virtual reality device and asking the humans to excite the motion of simulated robots. And we found out that for 1 degree of freedom, the law is very simple. If you ask the people what they do, they would answer, we are waiting until the torque is high enough, and then we are introducing energy by just giving a jump in force or in position. And this is simple for 1 degree of freedom. I won't go into details for more degree of freedom, but the essential idea is that one could save this concept to the multidimensional case by trying to identify the first oscillation mode of the system and trying to excite that and using this bang-bang controller idea. And to use that, or to achieve that, one uses an adaptive mapping between the n-dimensional torque and the one-dimensional direction of the principal mode. And this mapping is adapted by a learning technique. And then in this one dimension, tau z in this case, we excite the oscillation motion, and then we project back in the position space. And all in all, although the technology or the control law has been derived by pure robotics tools, it can be shown that this can be easily mapped to a neural network where you have a fan-in, fan-out configuration, and just with very few neurons, which, by the way, can be also trained with pure Hebbian learning, which is biologically plausible. With very few neurons, you can train to excite limit cycles without model knowledge more than kinematics information of the system, which is an interesting fact, actually. And this was the controller used to do the grinding task in resonance. And this is a simpler experiment just to show that the limit cycle is highly nonlinear. So indeed, we have nonlinear springs, we have dynamic couplings between the systems. And we hope that this idea can be also applied to designing running systems. We did some simulation work. We had several discussions with people already building serious elastic locomotion systems like ATH or Oregon University, and hope to apply this to locomotion where elasticity is probably most relevant. Well, with this I would like to come to a conclusion showing that we are at the point where I think the design of our robots is so close to human biomechanics and to human properties that we can really, by recreating these functionalities in robots, learn about the structure and about the control of humans, and at the same time use this knowledge to improve our robots and bring this benefit back to humans by doing better rehabilitation devices, prosthetic devices, and assistive devices. Thank you very much.
Hello, I'm Chan Soo-seo, a PhD student in Reconfigurable Robotics Lab at the EPFL. This ongoing work is the result of my colleague and my professor, Jamie Pack. I will be presenting a vibrotactile feedback actuator, which is made of very thin pneumatic actuator embedded sensor called SPSkin. Wearable device often needs to produce electrical, mechanical, thermal stimulation upon received external force. Among them, one of the safest and often used haptic is vibrotactile feedback. Using different pattern and intensity of vibration, we can regenerate the different tactile sensation in various locations in human body. Human skin can decipher a wide range of vibration and haptic feedback. This, of course, depends on surface and the material. Vibration is characterized by the combination of amplitude, frequency, and the direction of the signal. Currently, there are many kinds of vibration motor. However, the choice is limited, as most of them are very thick and heavy and have only one linear direction vibration. SPSkin is a novel vibration actuator embedded disputed sensor that can produce highly customizable, lightweight input-output devices for tactile feedback. SPSkin has multiple points of actuation, which are all embedded with a discrete sensor, here 5. They can not only sense its own vibration, but also it can measure external force as well. This SPSkin design can vary accommodate in multiple low configurations, so it can cover wider and curvier surface for actuation and sensing. This customizability allows SPSkin to be ideal for wearable robot and covering different locations on the body. This figure shows application on the hand and forearm, but you can easily see the application on the shoulder and chest as well. What is here is that the sensor embedded actuator with 5 actuation points. The frequency is 25. While the 5 boxes show the sensing location, they stay green and blink for each actuation and turn red for the external force. The main contribution of novel SPSkin is we have present a high intensive vibrotactile feedback hardware that remain highly flexible, lightweight, wearable devices, and distributed sensing and actuation allows it to be applied to many kinds of application. I'm so excited about this completely different vibration actuator, so I hope to see you in the interactive section. Thank you.
Good afternoon, everyone. My name is Ji-hwan Yu from Korea Tech. I want to introduce an interesting transmission idea that we are working on this day. Let's say there is a string or a bundle of strings. If you twist it, then it contracts. So by applying small input torque, we can obtain large amount of contraction force. So basically, string is kind of gear. And by coupling a rotational motor, one side, we can make actuator module, and we named it twisted string actuator in linear or rotational configuration. The TSA has several fascinating features, especially in robotics or exoskeleton kind of system. It is very light and also cheap and easy to replace, and can transmit the power over distance, of course, and intrinsically compliant and also backdrivable. And motor can be placed coaxially with axis of motion, so we can save lots of space in designing. And also can tolerate some misalignment, so can apply to soft and wearable exoskeleton system, wearable device. This is the first prototype that we have developed several years ago. It has weight of 2 kilogram and payload was 10 kilogram. And as you expect, it has unidirectional control limitation. So to overcome this, we proposed bidirectional elbow exoskeleton. And this video clip shows you an idea how this bidirectional elbow skeleton in action. You can lift it up heavy weight in reasonable speed. And by twisting and untwisting both of the wire string at the same time, we can adjust stiffness. So high stiffness and low stiffness. And one of the interesting feature is due to the backdrivability, we can easily detect human intention. So that can help us to triggering the motion of the exoskeleton system. In particular, in this paper, we have done some study on variable stiffness model because we know we can change the stiffness, but we didn't know the exact relationship between the amount of contraction and the stiffness variation. So we made a variable stiffness actuator module, and we have done some study about this. And as a result, we found a result that we can control the position and the tension independently. So if you want to know more, then I want to see you in my interactive session. Thank you.
Hi everyone, my name is Naoto Saki from Okaima University. The title of my presentation is Multiplex Pneumatic Actuator Drive Method based on acoustic communication in a spiral line. Pneumatic actuators have been widely utilized in various fields. However, pneumatic systems have many air tubes and many electrical wires. So conventional pneumatic systems become complicated to use many pneumatic actuators. To solve this problem, we propose a multiplex pneumatic actuator drive method. In order to realize this method, it needs two key components. First, acoustic communication system. Second, power supply device. Acoustic communication system makes it possible to control each actuator independently through acoustic communication in a spiral line. Power supply device generates electrical power from the energy of compressed air, and it realizes off-grid local controller. Therefore, it's possible to realize the miniaturization of the pneumatic system without electrical control lines. And this slide shows a prototype system developed by this method. Prototype system is shown in this figure. This system has air spiral line of 10 meters and is equipped with 3 local control modules. Okay, please look at this movie. In this experimental result, 3 pneumatic cylinders are independently controlled, and the power supply device also works well. Thank you for your kind attention.
At Disney, we are very interested in creating compelling interactions between people and robots. While human safety is an absolute requirement, we are not willing to sacrifice speed or expressiveness. To this end, we have developed a new type of passive hydrostatic transmission with either air, as in this arm, or water as working fluids. The transmission is leak-tight and low friction. This pair of 4 degree of freedom robot arms are identical and connected only by pneumatic tubing, without any motors, sensors, valves, or controller. The key element is using rolling diaphragms to seal the cylinders. They provide a hermetic seal, and their rolling motion eliminates static friction, in contrast to conventional sliding seals. We use pairs of cylinders to allow bidirectional operation, with the transmission fluid pre-pressurized to 1/2 the maximum operating pressure. This removes all backlash from the system. The transmission has very low impedance. There is no spring rate, and because of the transmission's symmetry and low friction, it is completely backdrivable. The transmission is used passively for remote manipulation, as in the robot arm, or may be motorized at one end. Since it is fluid-based, we achieve high torque density at the endpoint actuator. The arm or limb is much lighter than if a geared electric motor with equivalent friction and torque performance was located directly in the arm instead. With water as a transmission fluid, we achieve high stiffness and no lost motion between input and output. Fluid-based transmissions allow flexible hose and tubing connections and provide easy and adaptable routing. This transmission is capable of moving heavy loads at high speeds with very smooth motion. The end-to-end delay through the transmission is only 12 milliseconds. Under high-speed video, you can see here. The water-filled transmission achieves a force bandwidth in the tens of hertz. Combined with its high stiffness and low static friction, we find unexpected haptic performance. Surface textures can be felt through the transmission. Here are work loops obtained under manual manipulation. In red, we see high stiffness when the input is blocked, and in blue, the measured output force against a virtual spring. Forces are very smooth with a measured hysteresis of 6% full range torque and a maximum static friction of less than 1% full range torque. In the latest version, the actuators weigh 120 grams, can deliver 4.5 Newton meters continuous torque, and have 135-degree range of motion. Please come to our interactive session. We have brought the robot arm with us. You can practice your glockenspiel playing. Thank you very much for your attention.
Good afternoon, everybody. My name is Clem Matthijssen. I'm from the Vrije Universiteit Brussel in Belgium, and I would like to present the work of my colleagues and myself on the design of a novel intermittent self-closing mechanism of a McKibben-based series parallel elastic actuator, or SPEA. So the motivation of our work goes from the fact that humans are still outperforming robots in many ways, for example, their capabilities and efficiency, while on the other hand, the electric motor is actually outperforming human muscles, for example, regarding the power density and the maximum efficiency. So we come to the conclusion that the way transmissions and springs are used in compliant actuators needs drastic improvement, and we think the main challenges are the torque-to-mass ratio and the energy efficiency. So the SPA schematic can be understood as follows. We start from a standard SEA schematic. We add a bunch of springs in parallel there, and then we add D-phased intermittent mechanisms in parallel, which are shown here in yellow. So last year at IROS, we presented our first unidirectional prototype, which was based on mutilated gears. And today I would like to present a novel self-locking mechanism which will take care of the variable recruitment and locking of the parallel springs. The system is based on the McKibben Actuator, which was developed in our group 10 years ago. The McKibben Actuator is a variable stiffness actuator, so you can change the stiffness and the equilibrium position independently. And the virtues are the fact that there's only one spring, which can be linear, and the mechanism is non-complex. So my goal was to keep these virtues and transform this into an SPA actuator. So what we did was the lever arm in red. On the right is the newest system. We devised a guide that allows the lever arm to detach from the spring at the maximum deflection angle. As such, the motor is not loaded anymore while we still generate torque on the output. We did a model parameterization and then verified the model, as you can see in the bottom right. What we then did once we had this layer, we stacked up these layers, 4 of them, to make the first prototype. You can see in the results underneath that the load is cancelled over the parallel springs so that the motor itself is not loaded anymore, while we can still change the stiffness of the actuator. I would like to end with a video where you can see the working principle. So you can see that the motor is rotating continuously while the springs are intermittently or subsequently tensioned to the other side, and the self-locking mechanism takes care of the fact that each spring stays locked. So when the motor is at the outer position, you have the highest output torque, but at that point, the motor itself is not loaded anymore. So I would like to invite you to the sessions afterwards where I can answer all your questions. And I can already give you some insights of the work that we are currently performing while we are actually having this prototype to an updated prototype, which will be in the range of 30 to 40 Newton meters. So it's the next version. So thank you very much.
Good afternoon, everybody. My name is Nevio Tagliamonte, and I'm a postdoc at the Laboratory of Biomedical Robotics and Biomicrosystems at University Campus Biomedical in Rome. And today I'm going to present you work on a compliant actuator for biorobotics. More specifically, the aim was to develop a rotary parallel elastic actuator, and our proof of concept prototype was quite novel because it integrates a magnetic spring in the same design of the motor, and these allow a very compact architecture, which is also suitable to be up and down scaled. And it is also possible to produce resonant oscillations. And actually, to the best of our knowledge, our proposed solution is the first in literature in which compliance is intrinsically embedded in the actuator. So I don't want to go into details because we already listened about many talks about the importance of having compliance in the actuator for locomotion applications. So these are some examples. But in the two big families that we know, series elastic actuators are the most popular, but actually also parallel elasticity is very useful in producing efficient oscillation, like some example in literature. For example, in some insects, we have the parallel elasticity of the body of the insect that allow to produce elastic torques that helps the production of oscillation of the wings. So our actuator basically consists in a stator with windings and two rotors with magnets in a whole-back configuration, but the key idea is to add some magnets in the stator so that they can be coupled to the magnets of the rotors and produce elastic parallel torques that helps the oscillation like is shown in this video. So we also analyzed the dynamic behavior, which is quite nonlinear, as you can see from the graphs of simulation and also experiments. And we also explored some possible application. Here we added a tail to the actuator to implement a small robotic fish, but with some small modifications you can also achieve like a robotic wasp, which is quite different, but also can oscillate very well. Of course, it will be a pleasure for me to provide you many other information about the topic that I listed here during my interactive section. And in the meanwhile, please let me thank you for your attention.
Hi, I'm Wyatt Felt. I'm a PhD student at the University of Michigan. Today I'm going to tell you about work that I've done with my advisor to take McKibben muscles, or air muscles, and create them as self-sensing actuators. So for those of you that aren't familiar, McKibben muscles, or air muscles, are soft pneumatic actuators that contract axially when pressurized with air. Now, these sorts of actuators have been used to create all kinds of non-traditional robots. Take, for instance, this continuum manipulator developed at Pennsylvania State. Now, this manipulator is great. It can pick up large balls. It can pick up small balls. But with these hermetically sealed actuators that they have that are good to work in wet and dirty environments, they're still relying on traditional bulky encoders at the base of the manipulator. Here they have string potentiometers. So here we have an actuator that's well suited for these non-traditional robots, non-traditional environments, and yet we're using encoders that are vulnerable to those sorts of things and require traditional structures. It would be nice if these actuators could sense their own position and force output just as biological muscles do. Now, the way that we propose to do this is by taking that reinforcing braid that forms the contracting element of the actuator and making it into a circuit. So that is forming the braid out of insulated conducting fibers and connecting them together. And this way, the current moves along these helices, up the axis along one helice and down the axis along the other, constantly circling the axis in the same direction. So in some sense, we've created a solenoid. And if you look at the behavior of this solenoid as the actuator contracts, we can see the cross-sectional area expands and the length changes with the contraction of the actuator. If we look at the inductance formula for a solenoid, we can see that that increase in area and decrease in length both result in an increase in inductance of the system. So we're able to characterize this change in alignment in the actuator by looking at the inductance of the system. Now, in a method similar to a strain gauge, we can characterize the force output of the actuator as well. A load increase on this system results in stress in the wires that we can measure through strain through changes in resistance. So by measuring both the resistance and inductance of the wires, we're able to characterize the force output and change in length of the actuator. Now with the prototypes we've been able to develop, we've seen a high sensitivity linear response over the contraction range. And this has allowed us to characterize the contraction with sub-millimeter resolution. Now we're very excited about the applications that this technology could bring, the sorts of robots that it will be enabled to build with non-traditional joints. And if you're interested in learning more about our work or where we're interested in going with this, please stop by our booth at the interactive session. Thank you.
Good afternoon, ladies and gentlemen. My name is Edward White. I am presenting this work on behalf of my colleagues who were not able to be here today. This work was advised by Professor Rebecca Kramer of Purdue University and Jamie Pack from EPFL. Our motivation here is shown on the left. This is a typical knee brace. It's made of rigid components. It's large, it's rather bulky, and the opportunities for variable impedance there, or variable structural compliance, are fairly limited, and to enable that, it's a rather complex process. Our goal is to replace that with something smarter, as shown on the right. And what this is a fabric which is able to change its compliance through the manipulation of the material properties of the components of that fabric. And at the heart of that fabric is an SMA, or nickel titanium wire, coated with polylactic acid. The figure here shows our method of manufacturing that wire. We pull the SMA wire through a reservoir of liquid polylactic acid, coating it, creating a coaxial fiber. And as we heat that wire, we can change the PLA from a rubbery or a glassy state at low temperature, which is its stiff state, into a rubbery state, which is much more compliant. I'll draw your attention to the chart on the upper, upper right-hand side of this figure, and this is the results of a three-point bending test for a complete fabric sample. In the blue, you see the result for the material when it is in the glassy state, so look at the slope of that line, it gives you an indication of the strength of the material. When we transition it into the rubbery region by heating it, we go from the blue curve to the red curve, demonstrating a significant reduction in the overall bending stiffness of that sample. And just to look at the overview of this material in the bottom of the figure, the polylactic acid covered SMA is integrated onto the fabric using conventional sewing techniques. There's nothing particularly special here, so this could be integrated into lots of different types of fabric structures. In this case, it's simply sewn onto a piece of fabric. So to give you some idea of how this might be used, this is an example of a finger brace application where we're able to use the brace to hold the fingers in a particular location. Upon heating it, we can then move the fingers to a different location, remove the heat, and then lock the brace in place. And through that, one of the challenges that we're currently working with is that by heating that material, we do have a human interaction issue. We can cause burns, but it is something we're working on. Again, if you have any further questions, I look forward to entertaining them at the interactive session. Thank you.
Hi, my name is Sanaz Behbahani from Michigan State University, and today I'm here to talk about a flexible passive joint design for robotic fish pectoral fins. So I received a lot of questions asking why robotic fish, and to answer that in general, I have to mention fish has really interesting swimming behavior. They are maneuverable, agile, and efficient. That's why we're interested in studying robotic fish. And also in our lab, one of our main goals is to create a platform for underwater sensing for environmental purposes and also interact with live fish to study live fish behavior, which is good for biological reasons. So in this work, I focus on robotic fish that is actuated by the pectoral fins. And there are a lot of studies in the literature dealing with rigid pectoral fins and flexible pectoral fins. But the drawback to all of those which are connected to the body through rigid connection is that they may need different actuation speed for power and recovery stroke, and then they have 1 degree of freedom. So if you want to add another degree of freedom, you have to add another actuator, which would increase the robotic fish size. So we came up with a novel design for a flexible passive joint, which overcomes all the drawbacks that I mentioned before. And also, the joint is designed in SolidWorks and is 3D printed as one integrated piece. And the stopper there is actually what is enabling the robotic fish to have a symmetric power and recovery stroke speed. So we have to, we also modeled the robotic fish utilizing such a joint. The hydrodynamic forces on the pectoral fin were calculated based on blade element theory. The actual passive joint is designed is modeled as a pair of torsion spring and damper. And by having all the forces and moments on the robotic fish center of mass, we are able to fully calculate the robotic fish behavior. So we put the robotic fish under a lot of experiments to evaluate our dynamic model, such as like forward velocity, turning radius, and period. And also we focus on the flexible passive joint dimension and stiffness in order to optimize our design for the passive joint. And finally, we compared the performance of the robotic fish here, which has like the traditional rigid connection and our proposed flexible connection, and you can see that the robotic fish in the farther left is performing better. So I would like to discuss more during the interactive sessions. Thank you.
Hello, my name is Onika Aki from Japan. Today I talk about formulation and optimization of poorly gear type shape memory alloy heat engine toward microfluidic MEMS motor. This research is conducted by mainly colleagues of Yokohama National University and also supervised Professor Carl at University of Washington. So first motivation of this research is how to actuate the micro robot. One popular conventional method is remote manipulation by magnetic field as like capsule endoscope, like medical use. In this case, we control only one robot under monitoring. In our idea, the ideal micro robot should be like water flare. In this movie, they are less than 1 cubic millimeter, of course, and they propelled or moved their own muscles, their own actuators in liquid. And they move automatically and omnidirectionally with harvesting energy from their circumstances, such as food and sunlight. That is the point we think. So when we realize the fluidic microactuator, we think there are two main challenges. One is energy harvesting problem. 1 cubic millimeter is too small to install battery inside, so the actuator itself should have harvest energy and convert to kinetic energy directly. And they must work in liquid. So in this paper, we target the heat engine with shape memory alloy coil spring. As you can see here, the heat engine rotates strongly if they give them the temperature difference, hot and cool water. Unfortunately, there are no literature about how to analyze this kind of heat engine. So at the very beginning of this research, in this paper, we propose dynamical model and show the basic procedure of analysis from the first principle. And we finally get the optimal formulation that gives maximum power and torque. Let's discuss about perspectives of this heat engine at the interactive session. Thank you.
Hello, everyone. My name is Nick Eken, and I'm at the University of Pennsylvania with Dr. Mark Yim as part of the GRASP Lab, and I'm presenting my work on design principles and testing for a latching modular robot connector. So basically, we're presenting a connector for the purposes of physically attaching two robots or components of robots, in this case in the 2D plane. And this connector we're trying to design has high capabilities in terms of alignment and strength. So the alignment properties come from the shape geometry of the curves that you can see in the video, and the strength comes from the latching overhang. So it's got two layers that you can see there, and the effect of having the two layers is that you get wide alignment in both directions. And the reason we use passive mechanical geometry here is because we're trying to avoid complicated additions to the robot, such as power, actuation, sensing in the connection faces that can complicate the design. So if we look at why we're doing this a little closer, in particular, we want high alignment because in many modular robot systems, we're connecting and disconnecting frequently, and it may be at the end of a long chain in a chain-type modular robot, for example. In a chain-type modular robot, the errors accumulate according to second order, according to the number of modules. So this can build up rather quickly, and having a good way to correct the error without adding design complexity is very nice. So in order to understand the properties of the connector that I'm presenting, we've developed a new metric for these connectors called the bonding ratio, which is simply the ratio between the force required to disconnect and the force required to connect. This is important for our robots because we want to know how many modules it can actually support along the connector, as well as compare that to the characteristic force that the modules are able to exert. And then we've tested this in a tensile testing machine over several sets of design parameters and shown the strength and the bonding ratio for each. We've also demonstrated several scenarios, including progressive latching, showing that you can do it in like a zipper fashion and at the end of a long chain, and a control sequence to ensure a good latching fit. So you'll see in this video, this is a 12-module chain that successfully latches using the connector. And you can see it goes past the nominal latching point a little bit and then relaxes. And then that's just to ensure a good fit. So pretty much that's it. If you have any questions about the control sequence or the latching connector or the principles behind it, I will have all the information for you at the interactive session. Thank you very much.
Good afternoon, everyone. My name is Donna P. I'm a recent graduate from Clemson University, and I'm here today to present my work with researcher Dr. Gorege and my advisor, Professor Dr. Walker. This was an intermediate part of my master's thesis. The objective was to develop a new type of long and thin continuum robot which could be used for inspection and exploration activities, especially in space. The motivation for such robots can be said to be the endoscopes used in minimally invasive surgery or in nature like the anteater's tongue and tendril used by climbing plants. Their flexible and shape-adapting structures were emulated for the first time by NASA in its tendril, especially focusing on the unique sizing constraints. However, detailed study of tendril at Clemson suggested that structural improvements were essential in order to have a practical or application-oriented control. Hence, a detailed comparative study of the current state of the art was conducted. This study suggested that a superior design was possible by incorporating features of a concentric tube robot in a tendon-based design. This would help to provide local compression as seen in this video, along with multi-section bending, which is seen in continuum robots. Now, since this was intended for space applications, the actuation unit needed to be as compact as possible. Hence, springs were utilized in the design so that linear actuators, which is normally a bulky system, won't be needed. A simple motor encoder system, which was controlled by an Arduino, formed this compact actuation package. The kinematic modeling needed to incorporate the spring loading, and hence a compression factor was introduced in the established kinematics. In particular, in order to achieve the different configurations or shapes of the robot, it was essential to map the measurable quantities with the different shapes of the robot. For this purpose, experiments were performed with the cable robot hardware, and data was collected from the sensors and the robot shape. Linear regression was used, and it was found to be effective, and the results agreed well. Thus, in conclusion, the cable robot hardware is the first prototype of a long and thin continuum robot with a compact actuation unit and its forward kinematic analysis. I look forward to have the opportunity to discuss this paper further with you at the upcoming interactive sessions. Thank you.
Hello, everyone. My name is Ali Akbar from University of Buffalo. The title of my paper is the Kinetostatic Statistic Optimization for Adjustable Four-Bar Mechanisms for the Leg Wheel Subsystems. The articulated wheel robots, we are going to exploit the benefit of the both legged and the wheeled systems. With adding the articulations in this system, we increase the number of the degrees of freedom in the system. So this number of degrees of freedom has to be controlled. We can control them with the actuation and actively, or we can use a semi-active way or in the passive way. There are some challenges and opportunities. There's no systematic effort to design the articulated leg wheel system is ever considered. All of them are based on the intuition. And we are looking for the greatest motion ranges between the wheel axle and the chassis. And we are going to reduce the overall actuation requirements by a spring assist. And for enhancing the train accommodation, we propose the adjustable four-bar articulated leg wheel subsystem and active structural control to adapt system parameters to terrain traversal. Here we can see that's a four-bar mechanism that we use in our modified design. The first design was based on the four-bar mechanism, and this one is a modified design. And we can see that modified design is better suited to absorbing disturbances from the obstacle by moving up and away from the obstacles. And we go further and just focusing at the adjustable four-bar mechanism. So first, starting with the process of the design is first starting with the position and the velocity analysis, then going to the kinematic synthesis. In the kinematic synthesis, we are determining the length of the individual links that make up the mechanism to perform a desired motion generation. And then in the next level, in the kinetostatic synthesis, we guide the attached wheel through the several positions while supporting a set of the specified external loads. And then in the alternate adjustable design option, we focus on the adjustable ground link, adjustable rocker link, and adjustable coupler link. And finally, we found that adjustable rocker link and the adjustable crank link are so suitable and satisfy all of the criteria that we need. Thank you for your attention.
So, good afternoon. My name is Carlos Viegas, and I am a PhD student from the University of Coimbra. And today I'm going to present you a single degree of freedom arm for transition of climbing robots between perpendicular planes. So, climbing robots are very useful tools for inspection of human-made structures. However, they face some challenges because these structures are mostly three-dimensional. So they include obstacles such as ridges, flanges, gaps, and bends and branches. So the climbing robot must be able to overcome such obstacles. So our goal was to develop a transition mechanism which would be compact and lightweight and would enable the robot to overcome these obstacles. So to test our mechanism, we used this small and lightweight climber that we developed at our lab. So our concept was to use a system with two joints that would rotate simultaneously, and you can see the video here. Let me show you. One joint would rotate 90 degrees, while the second joint will rotate full 180 degrees. This could be easily performed with a single actuator and the transmission mechanism. However, these two joints should be derived with a time lag in order to avoid collision with any of the surfaces. So this is a detail of the mechanism we developed. I will explain you further the details on the interactive session. This is the magnetic attachment unit that we developed. It is capable of adapting both to flat and curved surfaces, and it uses magnets to connect to the surface. And here I'm going to show you a video of the mechanism in action. So this is all real time. You see the approach phase of the robot, then it connects to the structure, and then the transition phase. So I thank you for your attention, and please come see me at the interactive session. Thank you.
Hi, my name is Woo-Seom Lee from KISS. At this time, I'm going to speak about the safe joint mechanism for manipulator. The reason why we need safety mechanism is simple. First of all, we want to guarantee safety when we use robots in public area. Secondly, we hope to make CAN soft contact with us for safe interaction. Then the question is how to achieve our target. In our research, as for the mechanism, we made a flexible mechanism and release mechanism. The sensing function of the external torque was developed by measuring deflection of the flexible parts. So we can make a soft contact, and the impact force is reduced by using this flexible mechanism and external force sensing. And then the exit contact force could be cut off by the release mechanism. From this basic idea, we made the safe joint mechanism, and its name is VCSC. The flexible mechanism and the release mechanism are composed of ball and cam plate, and we use the cheap and simple distance sensor for external force sensing. This figure shows the structure of our mechanism. The flexible and release motion is generated by this ball and cam using the spring force. So we can design the suitable spring set and the shape of the cam plate to meet our target flexibility property and the target value of limit torque for the release motion. And we have one more plate, and this plate is contact within the other side of the spring. So if we rotate this plate, the pre-compressed length of spring is adjusted, and then the property of the flexible section and the release torque are changed. In our idea, the motion of this compensation cam plate is mechanically synchronized with the joint motion of the manipulator. By using this function, we can eliminate the effect of the changing gravity force when the position of joint link is changed. So the delta value of input torque to generate the release motion is maintained as a constant value. The motion VCSC is like this video. This video shows the flexible motion, and if we apply the torque is over the release limit value, the release motion occurs as in this video. When the angle of the base is changed, the pre-compressed length of spring is changed as in this video. Thank you for your listening, and we will have a detailed discussion during the interactive section. Thank you.
Hello, my name is Ronit Malka. Alongside Professor Alexis Lucier-Desbian, Yufeng Chen, and our advisor, Professor Rob Wood, and in conjunction with NSF funding, we tested and computationally verified a generalizable model for the stress on a flexure hinge. This model provides universal principles for extending hinge lifespan, regardless of a hinge's application or manufacturing method. Flexure hinges are becoming a very common application in both microrobotics and soft robotics. Our particular goal for them was for our lab's microrobot, the RoboBee. The RoboBee's wings are attached to a body frame and piezoelectric actuator via microscale polyimide flexure hinges. These hinges are cycled at 100 to 120 hertz and are given deflections of maximally of 45 degrees, making them relatively large deformation hinges. However, one of the main limits on the RoboBee's flight was the shortened lifespan of these hinges. Although the polyimide that they're made of has been shown to last on the order of 10 to the 7th cycles under similar loads, our hinges would fail after about 70,000 cycles, or about 10 minutes of flight. We suspected the reason for this was because of the asymmetrical loading on the hinge due to the wing flapping motion, which resulted in a much higher stress on the hinge. While many of the models and flexure hinges exist, they are highly application specific and are designed for injection molded hinges, which made them unusable for our application. Our solution was to use an approximation of the stress on a hinge assuming purely axial loading, in other words, ignoring the swiveling motion on the wing. The model had 3 main variables, which were hinge length, thickness, and angle of curvature. But since thickness and angle of curvature are limited by the RoboBee's flight mechanics, our study focused on the relationship between length and lifespan. Finite element analysis of the hinge modeling was validated using our previous model, which matched almost exactly with the FEA computations for the stress on a hinge with purely axial loading. When including off-axis effects, the FEA computation showed stress was greatly magnified, explaining why our hinges had been failing so quickly. A preliminary investigation showed great improvement in hinge lifespan when lengthening a hinge. Compared to other stress-reducing features aimed at minimizing the point stress on the corners, just lengthening a hinge by 40%, as is shown here, resulted in a great leap in hinge endurance. These results were verified in a more comprehensive study of many hinges with differing lengths, demonstrating a very strong correlation between increasing length and increasing lifespan. Following these principles, we designed a new hinge for the RoboBee that lasts about 30 times longer, or about 9 hours. Thank you.
Hi, my name is Aaron Dollar. I'm presenting work that was done with my student, Joseph Belter, at Yale University. And the concept is fairly simple. So we all know that 3D printed parts are everywhere and are becoming more and more ubiquitous. But there's still a lot of limitations into what you can utilize these parts for, in a large part because of the limited strength available in the materials for the more common 3D printed processes. So we wanted to see what we could do to improve the strength of 3D printed components without really changing the process all that much and retaining a lot of the benefits that 3D printing provides. And so the idea is fairly simple. We basically look to more to stronger resins and try to make composite parts essentially by filling voids in the components with these stronger resins. So as I alluded to, the essential process here is that you take the original part model that you might have printed solid ABS. We're looking mostly at FDM printers, and you design in some voids, either channels or meshes into the part that you then, after printing, go in and fill with higher strength resins in order to get a composite material, and we call this fill compositing. And so, the bottom image here just shows injecting a part with resin afterwards with the final part given here. So we tested pretty systematically a fairly large number of different options against the baseline FDM parts and the solid, a couple of different epoxies, as well as some different fill options, and I can tell you about the details of these. And we tested them all in a standard ASTM 3-point bending test on an Instron. And we also tested them, besides just these standard bar components, in some more robotic application components And basically, the result was a substantial increase, depending on the specific application, in strength and stiffness for these components. And it's a fairly straightforward process to implement. So the results were fairly good. So we can tell you more about the specific details and the specific results at our poster D118. Thank you.
Good afternoon, folks. My name is Ankur Mehta, and today I'll be presenting our steps towards a compiler that can automatically design robots based on a high-level functional specification. In this work, I'll describe our system that allows a user to quickly and intuitively code-generate mechanical, electrical, and software designs to create user-programmable robots on demand. First, let me share with you an email we received from one of our colleagues. In it, he requests a custom robot based on a loosely specified design. Typically, creating such a robot would require the use of several CAD programs, CAD and manufacturing tools, drawing from expertise across engineering disciplines in a potentially time-consuming and expensive process. Instead, we can identify the structural specifications with hierarchically composed library elements from our system, which can then simply be connected to form the final robot design. Though this image only displays the mechanical structure, the system also defines electrical components and wiring, microcontroller code for firmware drivers, and a high-level user interface, generating, in short order, fully integrated, directly fabricable designs for an immediately functional robot. More generally, a user starts with an idea for a desired electromechanical device and breaks it apart into functional elements. If these elements do not yet exist in our design library, then the process can recurse on the simpler functional elements, thus hierarchically building up ever more complex assemblies from a set of basic building blocks and previously generated designs. Once a satisfactory decomposition is found, the user assembles these components using an intuitive design script. This script is then compiled to co-generate the integrated, fabricable designs. This robot compiler is built upon a number of algorithmic and computational developments. A scripting language defining mechanical fabrication was extended to include definitions of electrical and software elements in a unified, functionally defined abstraction. This encapsulates the computation required to generate the fabricable designs from each parameterized module. These modules extend the design library of mechanical building blocks to also include discrete electric and electromechanical devices, along with firmware drivers, software blocks, and user interface elements. A collection of algorithms hierarchically combine these modules across subsystems to generate integrated, programmed electromechanical mechanism designs from their constituent building blocks. Finally, all the above are wrapped into an end-to-end system that allows a user to compile an assembly of mechanisms into a collection of directly fabricable mechanical, electrical, and software designs, yielding fully functional robots. This compiler was used to assemble our library elements into several different robotic designs, and I invite you to come play with our auto-generated robots as you learn more about this design system through our interactive session. Thank you.
Hello everyone, I'm Ryu from Rhythmica University in Japan. This work was done by my student Yuki Mishima. Now he is working in the Kubota Corporation. In this research, we treat a design issue of an actuated robotic finger with a special transmission. So recently, the design issue of an actuated robotic hand is a very hot topic for the application of adaptive grippers and prosthetic hands. So adaptive grippers are usually required to simplify the control method, and when we'd like to design the prosthetic hand, we need to consider about a trade-off between the decreasing the weight and size and increasing the grasping functions. So the conventional solution to design this robotic hand is to combine the several round actuated fingers, each of which is driven by at most one actuator. The requirement of those robotic fingers are to realize a connected motion in the free space like this, and to realize the adaptive motion when the finger contacts with the environment or object like this. So the typical solution of this unactuated design is to use a parallel link mechanism like this and to use a tendon-driven mechanism like this. In this case, we use a static equilibrium of the springs to determine that configuration. So, however, we use different approaches. The basic idea is to use special gear chains like this, consisting of that constant gear chain here and drive gear chain like this. As a result, we can realize that connecting motion like this in the free space without using a large actuation power, and we can also realize a connecting motion like this, adaptive motion like this, when the finger contacts with the object. And this design also simplifies the assemblies. So, and also we also bring that small mock-ups. So I hope to see you in the upcoming interactive sessions. Thank you very much.